3x3 systems of equations can be solved similar to the way we solved 2x2 systems of equations. Just like when 2x2 systems had equations in them, each of which represented a line, and where the lines crossed, that gave us our solution. When we have three variables, each one of these equations represents a plane in space. So what we have here are three planes in three-dimensional space. Something like this picture up here, right? And where the planes all cross at a single point, that point will be the solution to our systems of equations, right? If that happens, we call this system consistent. Okay, consistent when you have a nice solution like that. We're going to focus mostly on consistent systems in this class. However, you could also get situations where it's inconsistent. Okay, just like when we had two, for instance, parallel lines that never met, that would be a no solution situation. Here we have ways that we have no solution to our 3x3 system. And they could also be the same plane. They could be, two planes that intersect along a line but don't intersect all in one spot. There's a bunch of different ways this could go, but let's focus primarily on the consistent case where we have a solution that we can find, and let's focus on finding that solution. Okay, so here's an example. X plus y minus z equals -1. Negative 4x minus y plus 2z equals -7. 2x minus 2y minus 5z equals 7. All right, that's a standard 3x3 system of equations. By the way, these are linear equations, meaning that there's nothing squared, or it's not 1 over x or anything like that. These are all just single variables here. That's what we mean by linear. Okay, when you do this, it's helpful to label these as row 1, row 2, row 3. And when you go to solve these systems of three equations, you want to really take your time, right? The first thing you want to do is make sure that you copied it down right, because one little transposition error can throw off your entire calculation and it'll waste a lot of time. So take a second here and make sure that you wrote this down right, and do that on every single problem when you copy it down on your paper to start working on it. Make sure that it's actually copied correctly so you don't waste a bunch of time. Okay, what you do from here is focus on a single variable to eliminate, right? So look here, I have my y's are looking very similar. You want to find variables that are look very similar from one equation to another. So x would work here too. If you have like a single x or a single y or a single z, so in this one you could really work on all three pretty much arbitrarily. The y's are a little easier because they're already lined up right here. But certainly if you have a single variable, that's an indicator that you want to choose that one to eliminate. And the approach is, once you choose a variable to eliminate, you have to stick with it. So once you choose y, I'm going to choose y here, and I'm going to work to eliminate these y's, and then I'm going to work to eliminate these two y's together. What that will leave us with is a system of two equations with two unknowns. We're going to have x's and x's and z's and z's right there, and then we'll have the same thing. We'll have x's and x's, it's getting a little busy, and z's and z's down here, right? And we'll have a system of two unknowns and two equations. Let me show you what I mean. So we're choosing y and we're going to stick with it. So here we go. Let's do row 1 plus row 2. Okay, so and it helps to write this kind of nomenclature here to remind you what you're doing, and so it makes it clear to others what you're doing. So I'm multiplying just row 1 plus row 2. That's going to eliminate this y. So let's see what happens here. We have x plus y minus z equals negative 1. Negative 4x minus y plus 2z equals negative 7. Okay, I add them together. Negative 3x. The y's drop out as intended. Okay, plus z equals negative 8. All right, now let's look at row 1 and row 3. Okay, they don't quite line up, but we could do this. Let's do row 1 plus, let's actually multiply row 1 by 2. 2 row 1 plus row 3. If we multiply all of row 1 by 2, look what happens to the y's. We'll have 2y and negative 2y. They're going to cancel out. That's what we want to have happen. Okay, so you have to be really careful. Now I'm going to multiply everything in row 1 by 2. Alright, so let's see here. So we have 2x plus 2y minus 2z equals negative 2. Plus row 3. So now I'm just going to copy row 3. 2x minus 2y, look how those line up, minus 5z equals 7. Again, slow down with these problems and take your time. Otherwise, it's easy to make small mistakes and you end up dropping a negative somewhere or something like that, and you can spend a lot of time going down the wrong path. And then it takes a lot of time to find your error. So this is where you want to slow down, especially if you make a lot of small mistakes. Okay, 2x plus 2x, 4x. The y's cancel out. That's what we intended to have happen. Minus 7z equals 5. All right. And look what we have now. We have an equation here, an equation here. We combine these two together into a new system of two equations, two unknowns. So let's do that. Negative 3x plus z equals negative 8. And 4x minus 7z equals 5. New system of equations, and what we've done is reduce this to a simpler problem. Now, to solve this one, let's see, if we could just multiply this top row by 7, our z's would cancel out really nicely. So let's do that. I'm going to multiply this top row here by 7. And then add them together. So multiplying by 7, again, I'm being very careful. Negative 21x plus 7z minus 56 equals negative 56. All right, and then we're just going to leave the bottom row alone. 4x. Oh, and yeah, small mistake there. Whew, that was almost, that's how it happens. Not negative 27, but negative 21. There we go. And then down here we have 4x minus 7z equals 5. Right? Add these two together. What do we get? Negative 17x, the z's cancel out by design, equals negative 41. Okay, divide both sides by negative 17. That gives us x equals 3. One down. Okay. Now, to solve for the other variables, you need to plug back in. But if we plugged back in all the way at the beginning, that's too far, because then we have two variables and it's impossible to solve for these two variables. So you work your way back towards the beginning by plugging in an intermediate stage. So let's find a good place to plug in. I'm thinking maybe we can plug in right up here. There we go. Let's plug in there, and that will let us solve for z. All right, so we have 4 times 3 minus 7z equals 5. 12 minus 7z equals 5. Negative 7z equals negative 7, so z must be 1. 2 down. Alright, and now we go all the way back. Let's go all the way back to the original. Let's plug in right here at this top line here. So we have x and we have z. We can plug in now to solve for y. Alright, we're almost there. So 3 plus y minus 1 equals negative 1. A little cramped there. Let's go up a little higher with it. I'll bring it up here. So that gives us y plus 2 equals negative 1, so y equals negative 3. Okay, so y equals negative 3, z equals 1, and x equals 3. So it's helpful to write your answer as a single order triple. We'll do that as, let's see, x was 3, x was 3, y was negative 3, and z was 1. Alright, and that's a single point in space. With 3 variables, we have x, y, and z coordinates, x, y, and z. So if you were to plot that, it would be a single point in space where all 3 of these planes cross.